Uh, Hello, everyone. My name is Majid Salimi Beni, and I am a PhD student at the University of Salerno. Uh, in this presentation, I'm going to talk about our paper entitled An Analysis of Line-Tailed Network Latency Distribution and Background Traffic on Dragonfly Plus. Let's start with a question. If we take an HPC application and run it over and over, does it finish always at the same time? The answer is no, and there will be some variability in their performance, which means that some runs will be a bit slower and some will be a bit faster. This problem is known as performance variability. Performance variability is defined as the difference in the performance of an individual program in consecutive executions. Performance variability may originate from different parts of this HPC system workflow, like operating system, I/O, file system, MPI, routing, and more importantly, network. To show the performance variability, consider the left-hand side Dragonfly plus topology of Marconi 100 at Cineca Supercomputing Center in Italy. If we allocate some nodes to this cluster, and repeat running a communication-intensive program for 1,000 times and plot the frequency distribution, we will have a plot like this. In this example, we can observe that most of the runs take around 1.14 milliseconds, while some other runs are taking longer than the majority, that we call them long tail. In order to understand the impact of network in this variability, we allocate the nodes in 3 locality levels on this topology. The first one, all the nodes within the same group. Second, all the nodes within the same island. And third, nodes on different islands, which means that they can be allocated anywhere on the network without any restrictions. Considering the 3 allocation strategies mentioned, we take 3 collectives, broadcast, reduce, and alt-wall, and test them with 3 locality levels. For all the 3 collectives, when the jobs are placed on the same group, the minimum performance variability can be seen. However, when the nodes are allocated on different islands, the performance becomes highly variable, and the tail of the distribution, as you can see, becomes so long. So if the allocation on the same group is the most optimal case, why don't we always do that? Technically, we cannot always do so because first, there are a limited number of nodes within each group, and second, it requires a long waiting time in the job queue. Since we have to wait to find a totally idle group of nodes to allocate them. By default, most of the times, the scheduler will allocate the nodes on different islands for our program. So in the rest of the presentation, all the allocations you will see in the plots are related to, are done on different islands. But what makes the performance of different island allocation strategy more variable? To answer the question, we need to consider network, which is a shared resource among all the users of the cluster, and it's been identified as the main source of performance variability in the previous work as well. To have information about other users' activity on the cluster, we collected data from the job scheduler in a 3 months time frame, which is the only available information in the user space. And according to the information we collected from the scheduler, we proposed this heuristic to estimate the network congestion on the network. We call this heuristic background traffic. And in simple word, it's the ratio of nodes contributing to communication to all the physical cluster nodes. Using Pearson and Spearman correlations, we showed that the heuristic is around 80% accurate for different collectives. And also the correlation becomes stronger for larger message sizes, which means that the communication time is highly affected. It's highly affected by the background traffic while transferring larger data sizes. Here we show the performance of three microbenchmarks while there are different background traffics. As shown for all of them, when the background traffic is higher, the performance becomes more variable and the tail of the distributions become longer. Also all-to-all, uh, the tail of the distribution is longer than others, especially when the network is more congested, which is because of its higher communication intensity. Another interesting point here is the bimodal distributions of reduce and all-to-all under higher background traffics. The reason for this dual peak distribution is the adaptive routing algorithm that passes some packets through the minimal path, and when the minimal path is congested, uses another alternative path for doing the data transfer. So the first peak of the distribution is related to the minimal path, and the second one is related to the non-minimal path. So far, we focused on microbenchmarks, but here in this slide, we show two applications' performance under two different background traffics. Applications are mainly consist of different communication patterns and some computation, but still the background traffic, as you can see, will make their performance variable, and it shifts their distribution tail to the right when network is congested, which means that we need to care about congestion when running an application. To conclude, overall, we did a comprehensive performance variability study on a cluster with Dragonfly Plus network. In this study, we considered different communication patterns, message sizes, job placement localities, and background traffic. As a future work, we are going to gather more information from the network and use some machine learning models to make our heuristic more accurate. And finally, apply our findings to the scheduler to make more accurate scheduling decisions. At the end, I would like to thank you for your attention and also thank the conference organization for their perfect organization. Thank you.